Welcome back. Welcome back to class 12. We are today talking about mediation. And this is a very exciting lecture, essentially, and very exciting topic, which is quite central and quite important for all kind of epidemiological studies. So, I'm showing the wrong screen here, I think. Okay. No? Okay. That's fine. Okay. So what we're looking at today is at class 12. We have the RMD file, just as usual. We have, in addition to that, we have 3 different publications that you can see. So let's open the PDF. As I said, class 12. We will be talking about 3 different papers. One of them is my paper, which is essentially a paper that outlines the general approach to mediation, discusses potential outcome and potential mediator concepts, and also discusses sequential ignorability assumptions and the identification of mediation. So, secondly, we will be also discussing the Breda paper. The Breda paper is essentially was a psychological approach where they actually conducted an experiment investigating the effect of emotions, anxiety about some certain racial and ethnic groups, group cues, and to what extent people felt threatened by immigration and would react to that. So we'll be using these 2 examples essentially to discuss mediation. The McKinnon paper, and I will refer to this later on in the lecture, is essentially a paper showing the different approaches and outlining the classic approach. And you will see this in the lecture. Okay, so we will be talking today about causal mediation analysis. We will be distinguishing between indirect effect and direct effect. We will be discussing the classic approach. That comes, it doesn't come from there, but it's nicely outlined in the McKinnon paper. We will talk about linear structure equation models and the associated limitations to this approach. We will be talking about modern approaches as outlined in the MI approach with the potential outcome and potential mediator concept, the sequential ignorability assumptions and the identification of mediation. We will be talking about the Bredas and the immigration studies, and this will essentially lead to us. So we'll be briefly talking about the study design and hypothesis underlying this paper that involves mediation, emotions as the mediating factor that essentially does associate to the outcome of the study. In this context, we will be using the mediation package from R that will allow us to run mediation analyses and essentially determine and compute various factors outlining total direct and indirect effects. Then we will be briefly talking about the interpretation of that. And in the lab, we will be talking about the iris example, which essentially gives us an idea why irises are pollinated by bees or not, depending on the aesthetics of the iris flower or bloom. So we will be talking about non-unmeasured settings and model misspecifications. Good. So let's get started with the lecture. So I'm doing a full screen. So essentially what we're looking at is this outline. And now in principle, just as a recap from your EPI studies, what is mediation? So this is a directed acyclic graph, which you certainly have already discussed in your EPI classes. So essentially, you have a predictor, one exposure, that points causally to an outcome, the criterion Y. So X causes Y. So now X causes Y. So there's a total effect, essentially, which is the entire causal association between predictor to outcome. This includes all mediating factors. To go back to interaction effect modification, this also would include all effect modifying factors. So only the identification of these covariates that essentially do have an effect modifying or mediating effect will allow us to separate into direct and indirect effects. So essentially the sum of the total effect is, now the total effect is the sum of the direct and indirect effect. So this being said, we have here in that causal pathway between predictor exposure to outcome or criterion, we do have mediators. And these mediators can be partial mediators, full mediators. So there are various different concepts. To go more into detail, I refer to the EPI classes where more of the concept is being taught. We are approaching this today essentially in a rather statistical manner. And we will be using, as mentioned before, we will be using these with 3 examples, where we have the more modern approach in the EMI paper, where we investigate a job training program participation and the effect on depression with the mediator of job search efficacy, which is on this causal pathway between program participation on depression. So this is treatment, outcome, mediator. Then we have media's impact on political action from the Breda paper, as I mentioned. So we have news article to action taken based on this effect of this exposure of that media article on an individual, mediated by emotions towards a certain racial or ethnic group. And then we will be talking in the lab, we will be talking about the iris septal length on the status of being pollinated by a bee. And the mediator essentially here is the attractiveness of the flower, which is a super interesting topic essentially when you think about it. So it's a new one. It's not public health related, but it illustrates nicely where we're going with this. Okay. Analysis objective. So we're having an indirect and a direct effect of the treatment variable on the outcome. So this is what this is all about. Total effect is the sum of direct and indirect effect. So now when we look at this in the context of the classic mediation analysis, and this is really where I'm referring again to the McKinnon paper. So we have this linear structural equation model that essentially determines here an outcome model, which is essentially nothing else but a linear regression. So we have an alpha 1 as our intercept. We have a beta 1 and an x. We have a xi confounder, xi 1 confounder. So this is the letter xi. I hope I'm pronouncing it correctly. So it's essentially, it's the Greek C, and this is what's chosen here with the C. So it's xi 1 C plus epsilon as the error, residual error term. So you don't need to know the Greek letters, but I think it does make sense that you know for these kind of mathematical annotations, it does make sense that you at least have a vague idea how do those look like, how do you pronounce them, and how do identify which letter this actually is. So, you know, alpha, beta, and you have xi, then there's gamma, there's delta. We will see a delta later on, and here's the epsilon as the residual error term. So this is our general outcome model, right? So this is what we've seen already in the past. If this would be gender, for example, as a binary outcome, we would have the difference being contained here in the difference in this continuous variable y would be essentially contained here in this beta. If x is 1, we get this added to our predicted outcome, continuous variable. And if it's 0, this drops off, and then we just get the non-present, that counterfactual effect on the y. So now when we include the mediator, so now we, in addition to that, we're predicting the mediator. We're not predicting the outcome anymore, we're predicting the mediator. And this essentially is done again with an intercept. We're again going back to, and I'm showing this again. So this is now this pathway that we're depicting, x towards m. So this is the outcome, x to y. This is the mediator, x to m. So we're getting now to m by having again an intercept, beta to x, xi c, and a residual error epsilon. This is the mediator model. So now when you combine now mediator and outcome, you essentially get, you get arithmetically derived. You get an alpha 3 as the intercept. You get a beta 3, which is now a new coefficient, predicted coefficient, beta hat 3. We get now a gamma mediator. So now we're including the mediator, so it becomes an additional coefficient. And we again have xi for confounder, which are the additional confounders that you will find. And we have a residual error. So logically so far, right? So we're combining it now. And obviously this m will be determined by this equation 2, whereas the rest of this will be determined by that. So now we have here a classic model. We have the mediator predicted, but now we can, so we have a beta 1, which is this guy, beta hat 1 and beta hat 3 here is essentially now the total effect and the direct effect. So this is, we have x on y in its totality here. We have x on y with only the direct effect, accounting for that mediator and subtracting and distinguishing between mediator effect, indirect, and the direct effect on exposure. So we can exclude this indirect effect now, and we can only account for this direct effect, which is directly x acting on y on the outcome. So now arithmetically, this is obvious. And now we have a beta hat 2 multiplied by gamma here can essentially be conceptually, or not only conceptually, actually arithmetically be reduced to beta hat 1 total effect minus beta hat 3 indirect direct effect. And so this essentially becomes then the indirect effect. So the approach, so once again, beta hat 1 total effect, beta hat 3 direct effect. The difference is the indirect effect, right? So this is beta hat 2 multiplied by the gamma hat. So this classic mediation approach suffers now obviously a little bit from limitations. One is it is essentially designed for continuous data. This, of course, can be extended into discrete data, but not very easily. And it's also, it kind of does really establish a formal causality. So it is kind of pointing towards causality, but it does not formally allow to establish causality between mediating effects. So if we're going now back to potential outcomes, I hope this was clear so far. I think as a concept, this is considerably easy. And again, you must have heard this already in your epic classes. If not, you're hearing it at the same time with this case. Okay. So now let's assume xi is a binary treatment variable where xi equals x, where x can be 1 when an individual is being treated, or x equals 0, which is the counterfactual, right? So counterfactual means it has to be either one of them. So if you have a randomized controlled trial and an individual is either not treated or is treated, there's not really any other way to that, right? At least in the simplest version and intention to treat analysis. So when we're using now yi with the condition x, it's either 1 or 0, to denote the potential outcome that would result on the treatment status. So we're predicting this for each individual under each condition. So yi1 measures an individualized outcome if he or she is treated. So we have done the additional covariate in the models that would essentially say, okay, we have an individual that is 42 years old, is female, is I don't know, of African American descent, is not Hispanic, smokes 2 packs of cigarettes a day, I don't know, drinks half a bottle of vodka a day, and essentially has a certain risk of that outcome. Okay, I'm just coming up with any kind of example, but essentially it is all these covariates will basically lead to estimating an individual's outcomes when he or she is treated with whatever intervention you employ. If you have yi0, you essentially measure an individual outcomes for the same covariate sections if he or she is not being treated and is in the control arm. So either one of them needs to be present for the x, meaning that is a counterfactual concept. So the treatment effect in such a setting can be derived by yi1 minus yi0 for this particular individual. So this will be the individual effect that you can observe, that you are likely to observe following the accuracy of your model. So we define this potential mediating now as mi1, where the value of the mediator is if I is, so this individual I is being treated. So again, so this mediated indirect effect is now also underlying the condition of whether the individual is treated or not. So we can now define mi1, mi0, and by that essentially we get a value that will be associated as the coefficient to this mediator if the individual is treated, or in the counterfactual if it's not treated, if the individual I is in the controlled arm. Therefore, yixm represents the potential outcome if the treatment exposure and mediating variable to x and m respectively. So we're getting now for yi, we're getting a certain outcome estimate, outcome probability, outcome, whatever the variable is that the outcome represents, and it will be affected by the mediator. For the example of IMI, we're looking at yi of 1, 1.5. So 1 is now x, so this is treated, yes. 1.5 is the mediator. So this is the degree of depressive symptoms. So it's, again, let's recap. IMI was job participation program, direct effect on depression, mediated by job search efficacy. So we have the degree of depressive symptoms or the degree of depression, whatever score scale you're using, that would be observed if worker I participates in the training program and has a job search, a self-efficacy score of 1.5. So this is what this would imply as a potential outcome. So this indirect effect is now quantified as delta. So this is the delta sign, delta I x. So this difference, this indirect effect, delta I x for the condition of I, where yi is x mediated for the condition, for the counterfactual condition 1, minus the yi x mi in counterfactual condition 0. So we have x equals 0 or 1. So not treated and treated, right? So it's an effect of mediator on potential outcome while holding the treatment status at x. So essentially what you do, does this sound familiar? Yes, it does sound familiar. You remember when we had 0 and 1 conditions with gender, then essentially we're able to calculate the difference and use this coefficient to essentially think of this as the difference between the groups. So now we essentially, again, we're coming to either 0 and 1. So we're holding now our treatment status constant. So we're saying, okay, so this is X. So this is a non-treated individual. This is a treated individual. And by essentially expressing mediator for condition 1 versus mediator condition 2. So this is, again, this is following a certain model. You're modeling out this mediator. And if you're holding the treatment status now constant, you essentially can arithmetically derive the indirect effect used and not used, but deriving from the mediator. So this obviously you can now also use this for the quantification of the direct effect, right? So now you are quantifying this at phi. So you are essentially now looking at the direct effect of exposure to outcome. So phi x is now essentially yi for 1 when the mediator condition, the indirect effect, so this is the indirect effect, which we model, right? When we hold that constant, minus the yi for treatment status 0, where my I is consistent with my I in this term. So by that, you're holding now the mediator constant and you're changing only the treatment status. By that, you get the difference between treatment status and treatment status negative. So you get intervention versus control. So this difference is phi I x. So this is our direct effect. So we're holding now the search self-efficacy constant. And by that, we essentially were getting the direct effect of the participation in this program. And if you are setting this to 0, so this is where you are not participating. And this difference is now, this is our treatment effect directly, taking out this mediating effect of whatever this mediating effect is. So by that, essentially, you're taking out this effect. What's the difference to a confounder, you're going to ask now, right? The difference to a confounder is that now the outcome does not associate directly in a causal way to the mediator. So you remember when you have a DAG, you have exposure effects confounder, outcome affects confounder. So now in this setting, you have an effect. So if you have, for example, if you have age in a way, right? Age is classically confounder, gender. These are basically non-modifiable variables that associate with both exposure and outcome. But now you have something that is independent and does not essentially it is also non-modifiable, but it's not caused, but it associates in a how should I say, in a causative manner. So you have now, when you look at this pathway, when you look at this pathway of exposure to outcome, and you have job search self-efficacy constant, this would not associate with the participation in the training program, because it's randomized in a way, right? So also in the other way around, so there's no clear association, but it's something that mediates the depression score. So it has an effect, and it takes part of this direct total effect of the exposure on the outcome into its effect, right? But it's not causally associated. So now, arithmetically, it can be taken out now while you're taking that indirect effect that you have on that mediator via that mediator on the outcome constant. So by that, you can calculate and you can quantify only this direct effect that is not passing the mediator pathway. So now we're getting a little bit more to the newer ways and more modern approaches to this, which is the so-called average causal mediation effect, aka averaged indirect effect, and the average direct effect, ADE. Then these are simply the means, the expectations of the unit level effect. So again, you have now for each individual, you have a certain outcome probability and or outcome magnitude, independent of what it actually is now. So essentially, you get the average causal mediation effect X. You get an expected. And again, it's expected, right? So this doesn't mean it's really going to be found. You look retrospectively as data, you may not really have found it, but based on the model, you're expecting delta I. Again, this is the difference. This is the indirect effect. You find a delta I X that is an expected. Again, E for expected, right? You may remember this from the mathematical connotation of the chi-square test in your introductory statistics. You have expected minus observed, so E minus O. So E stands for expected YI. So this is the individual outcome for X MI1, where we have treatment condition 1 for the mediation. Minus YI, X is constant. This is now either 1 or 0 for in both terms. And by that, you get the differences between the mediators only. And this is your averaged causal mediation effect, which is essentially quantifying it for each individual and then averaging over the entire group of your sample population. In contrast to that, you have the ADE, which is the average direct effect. The ADE is the expected phi IX. So this is this direct effect of exposure to outcome. And you have an E, you have an expected YI1 with MI now as being constant, minus the YI0, MI with X constant. And the same is in the term here. By that, you get the difference between the treatment effect only conferred by the direct pathway. It's subtracting the effect from via the mediator, this so-called indirect effect. I hope that was clear so far. I think as a concept, it's considerably straightforward. In its interpretation, it gets a little trickier. No, it's actually not that tricky, but it's a nice way to express it when you really assume that there is mediating effect. And the identification of these mediators in large complex networks, and there was a question yesterday in a quick review session that I did last afternoon, came up. It's like, when do I know when to use interaction, for example, interaction effect modification? You don't really know. There are some pathways that you can choose to identify whether there's an interaction, but there's really no golden statistical rule that you can say, okay, so this is now an effect modification. You kind of know for the confounders, because you see to what extent coefficients change when you include the confounders, and that's a healthy way to kind of look at this. The same with the effect modification, where there are changes after inclusion of this covariate, then you may conclude that it may be better to kind of think of interaction in this context. But a lot of this is basically just derived from the underlying, I always come back to my world and I say pathophysiology or physiology, which is true in the context of biological variables, but then there are other situations where essentially you really need to base it on what you know from the literature. And this is also true for mediation to some extent. So there are some identification ways, and we will chat about these, and you will see them also in the paper. So I encourage you to use the paper. So Professor Seng has put together, first, these are great slides. And secondly, there are also really good example papers, and I really encourage you to read those to learn more about mediation. So in the R package mediation, you get for binary treatment exposure variable, you get the output for ACEMT. So this is the average causal mediation effect with 2 rows. And what's different? So you've seen how you approach this for a continuous variable. This is when you can use the classic approach from the McKinnon paper. Here you have a binary treatment exposure variable, and it gives you a better approach for categorical variables. So you have ACEM control for x equals y, ACEM for treated for x equals 1. Similarly, you can approach it for ADE and the average direct effect. And you also get outputs that you can essentially look at later. So what's important here is that the idea, and this is obviously, this is very obvious when you think about it. So you have a total effect, and now you get a direct effect and indirect effect, and the sum of this is the total effect. What you obviously need to be able to exclude at this point is, and this is likely the case if you look at a randomized setting, for example, but in some cohort settings it may not be given. So this is when it becomes tricky. So you are operating under the so-called SI assumption. This is the sequential ignorability assumption. Means that we have no unmeasured pre-treatment confounders, and we have no unmeasured post-treatment confounders. So the pre-treatment confounders mainly for treatment and outcome. So this is where randomization comes really into place, right? So essentially we have treatment and outcome needs to be not confounded. So which is kind of given in a randomized setting in cohort studies problematic. If you have this in there, so this is where we go back to that Xi-C. We have to kind of try to get them out. And this is just not possible in the more modern approach. As you can see, this is really kind of going directly at this association, right? So it's a little bit more tricky. There's some workarounds, but this is beyond the scope of this class. Non-unmeasured post-treatment confounders for the mediator as well as for the outcome. What does that mean? Well, there could be, for example, something that makes patients drop out and creating thus a selection bias. as a statistical collider, right? It's a collider, not a confounder, but essentially something along these lines you should be thinking, right? It's like if I give a blood pressure medication at the same time I start a sodium restriction regimen, so both of these will interact. One may act as an indirect effect because the blood pressure medication may be more effective when it's not in the presence with sodium restriction, or you can't have as much sodium intake when you take a certain medication. So think of this along these lines. So if somebody is then very, very strict with this sodium restricted diet, he may also experience blood pressure drops that are kind of not good for him or her, and may, but as a consequence, so him or her may not have good tolerability of the blood pressure medication, may not take the blood pressure medication. So there are some many dimensions that you need to take into account, and in its entirety, you have to find ways to kind of justify that there were no unmeasured post-treatment confounders. So the identification, okay, for both mediated and outcome. So the identification property allows the statistical estimation of the quantity, is not based on a specific model, therefore capable to implement for various discrete data types. So this is now essentially the beauty of these more modern approaches. And this essentially allows for us to also look at discrete data, which essentially puts it a little bit superior to the linear structure equation model that we've looked at before in the classical fashion, which was limited to continuous data. So now the Brader paper. So I really leave it to you to read this in more detail. It's a very interesting paper, and it basically investigates immigration attitudes. So the Brader studied. Brader studied 354 white non-Latino adults, randomly sampled from 46 states nationally. 52% were women, so nicely balanced in terms of gender. 31% identified as Republicans, 28% as Democrats. So this is a little bit of a, okay, so so this is nicely balanced as well, but emphasizes downsides of a two-party system. Median age was 46 years, with some college attended in most of them, and 45,000, as far as I recall, it's a median household income. Okay, so we have a media interview conducted over 16 minutes, seeking the reaction. The reaction here is willing to write an anti-immigration letter to a story that happened in the news lately. So what was interesting there is that the story was toned towards following ethnic, so perception towards certain ethnics. So this was either the individual was determined. So this is where ethnic basically comes into play, where Hispanic ethnicity and European ethnicity essentially had differences. So when confronted with Hispanic ethnicity, respondents were more likely to write a letter to Congress to ask for stricter immigration policies, but when it was for Europeans, they were actually more likely to request more information about the newspaper article. So it's, yeah, so it's an example of ethnic perceptions and how people react to ethnic perceptions in the context of whatever they have read and seen in anxiety-provoking newspaper articles. So now the idea behind that study was whether changes in ethnic perceptions impacted opinion and behaviors, with emotions being the mediator. So the hypothesis was that information seeking and political action should be more likely to the extent news about immigration arouses anxiety. So anxiety per se should mediate those effects. So the emotion caused by news articles or news contributions is mediated by anxiety as an emotion. So we have now a data set from the mediation R package, 265 subjects, 15 variables. We focus on 7 variables. We have Congress, anti-immigration message to Congress. We have treatment. This is the ethnic and perception factors. So this is our actual interaction term. We have emotions, so that's measures of subject negative feelings during the experiment. Numeric scale between 3 and 12. 3 indicates most negative feeling, 12 the best positive feeling, or the least negative feeling. Age, education, gender, and income. For the hypothesis, anxiety, the emo variable as the mediating variable, was put into this framework as the causal effect. So the authors first fit a mediator model where the measure of anxiety, emo, is modeled as a function of the framing treatment, treat to Congress message to outcome. We're looking first at the mediator model where we're essentially looking as a function of the framing treatment, so treatment to emo, adjusted for the pre-treatment covariates that will act as covariates adjusted for to minimize confounding. Then we fit an outcome model where the outcome is binary variable indicating whether or not the participant agreed to send a letter about immigration policy to his or her member of the Congress. The explanatory variables have included mediator treatment status and the same set of pre-treatment variable as used in the mediator model. So you see already where this is going. So we're doing the same. We're doing essentially now, we're setting treatment constant. So this is now treatment. We're getting mediator predicted for each individual with constant treatment. By that, we essentially will get under the treatment condition 1, we get a mediator estimate. We get under treatment condition 0, we get a mediator estimate. The difference of these is now our indirect effect. That's the averaged causal mediation effect, the ACME. So now that this is a quote unquote indirect effect trend. And now we are basically coming also to the overall effect, which is our ADE, our average direct effect. So it used the same pre-treatment variable. It used the same pre-treatment variables, and as such, it basically will allow to have comparable situations. So we're using the same different set of covariates depending on causal inquiry. So you can basically change the variates and the covariates for whether you're predicting a mediator or an outcome model, but that really is dependent on your causal question and to what extent you think this is a confounder for the estimate of the mediator only or estimate for the entire password. So the R code is library mediation. We are getting here mediator fit, which is nothing else but a linear model. We have emotions as a function of treatment, age, education, gender, income. We get now an output fit, which is message to Congress as a function of treatment, emotion, age, education, gender, and income. Data is framing, and the family is binomial. So this is logistic regression, essentially, where this binary outcome, message to Congress or no, is essentially put in the context of the pre-treatment variables, and the treatment variable per se. So now we get a mediation fit, we get an outcome fit. So now in the next step, we are using the mediation package. We're getting a mediation out, which is mediate, mediation fit, the model from before, that's the linear regression, outcome fit, which is our logistic regression. Treatment function is treat, mediator is considered emo. We are adding a non-parametric bootstrapping with 1,000 simulations. So this is like repeated random sampling for up to 1,000 times to essentially artificially inflate the sample size and to create a more robust estimate for the thing. So that's bootstrapping. So you will probably in one of your advanced classes, you're going to be exposed to these kind of approaches. So you have bootstrapping as one of these approaches. So you create replicates of your analysis, and by that you get a more robust estimate. But this is like a very casual way to speak about this. There's obviously much more involved to that. So so you have methods like bootstrapping and jackknifing, and that's the beauty of R. And R allows you to do this super simple. And keep this in mind. So you may choose this to do this hypothetically down the road for some of your analysis, or maybe consider it for your master essay or for your capstone. It's a very elegant method. In the same context, you could also employ Monte Carlo simulations. So there are various ways to go into this down this pathway. So mediation does exactly that, and with bootstrapping, essentially, we are getting now to these outputs, which essentially allows for us now to estimate the actual mediation effect. And we are seeing an averaged causal mediation effect for control and treated, which is almost like consistent. They are all significant. In addition to that, it gives you a confidence interval that allows for you to properly report them. And you can basically here quite elegantly display your indirect effect, your total outcome model. This is the total effect. This is the indirect effect. This is the direct effect. And you see already that this adds up, right? So you can calculate this from your effects that you have within the certain group, right? So if you are calculating now treated and control, you get the sum of direct effect and mediated effect is essentially adding up to this total effect. So preserving this framework that we have discussed about, or maybe some rounding difference, but essentially that's what it is. So the estimated ACME is statistically significant from 0, but the estimated average direct effects are not. Why is that? Well, because the framing experiment may have caused increase so think of it in that way. You have a mediating factor that is on the causal pathway of exposure to outcome. And you see a total effect that is essentially, it kind of points towards, it could lean towards making an effect. And you may see in your logistic regression, you may see an effect, right? I don't know. If you do not see this effect, so you have a p-value of 14%, you have a 10% increased total effect here, essentially, almost 10%. So what this would imply here, that the direct effect after taking the mediated effect out of this equation essentially is so marginal that the news effect per se is essentially virtually inexistent. But if you look at the mediating effect, it's really that emotion that has triggered the individual to write a letter to Congress or support writing a letter to Congress. So this obviously changes the entire interpretation of that data. So, and this is where it's really getting interesting, because it allows you to kind of evaluate more of the causality on that pathway. And I think this is how you can, to some extent, think of mediation a tool where you get, even from observational data, or here this was, no, it was not randomized data, but it's in a randomized data set, you are more likely to kind of evaluate causality within your pathways, and to evaluate causal pathways that essentially did alter that direct pathway from exposure to outcome. And yeah, so let that all sink in. Watch the lab, see the lab, play around with the lab yourself, and find out whether irises are more likely to be pollinated by bees when they're ready. And so essentially, think about this, how powerful that can be for many of your research questions. So all this being said, that's basically all what we had for today, for the lecture part of it. So now we still have the lab. So I will post a separate video for the lab. So we have the iris example with the simulation. So please check out that link. I will refer to that in the lab. And we essentially have from Matthew Fuchs simulated setting under no unmeasured confounders. So this is essentially what we did just before. So we will do the mediator attractiveness is simulated as 35% contribution by septal length, 65% random noise. So we will do that in the lab. The outcome Y, like you be pollinated by a bee, simulated similarly. So then we will run this experiment in the lab. So this is what we're gonna do. Then you're being asked to redesign the simulation with a certain portion of mediator and a certain portion of the dependent variables coming from a confounder, e.g. the pedal width variable in the iris data. So rerun the mediation analysis under using the Matthew Fuchs mediator model, the outcome model, the misspecified model, and then using the correct model with confounders added. Compare 1 and 2. And comment on the results upload to Blackboard. So this is lab 12, and I will be back in a bit with lab 12. All right, thanks so much, and I hope this was insightful, and let me know if questions, post them to the discussion board. Also, research note 12 is research note 2 is assigned. You should see it out there on Blackboard. And please also make sure that you read the papers. And yeah, homework 2, I know I'm still lagging behind with the grading. I'm still working on that. I will come back to you all very soon. And we are doing our last class next week. And then we're basically done with theory. Homework Tuesday and you, which posted a little late, so I have pushed this a little back. So this is actually now 12/2/2021. So you got an additional day, an additional 3 days because it was 3 days late. And yeah, XM2 1206, and then the research notes 2 at U1213. All right, thanks so much, and let me know if questions on the discussion board. All right, bye-bye.